Okay, any questions before we continue? And what we had done was we looked at the first law. Okay, one application of the first law was we had derived the adiabatic law for the ideal gas. This is constant for gamma is equal to 5/3 for the ideal gas. Then we calculated the work done in various processes. We looked at the isothermal process. Which is T is equal to constant. Then we had the adiabatic process. Where we had delta Q is equal to 0. And this led to PV to the gamma is being constant. And in an isothermal process, what we will be using today, and we had seen that, well, since T is constant, at least for the ideal gas, since the internal energy depends only on the temperature, delta U is 0, and the heat given to the system is equal to the work done by the system, which was equal to nKT logarithm of the final volume divided by the initial volume. Now we are ready to make an engine. What we expect from an engine is that it should just keep on working, repeating the same thing over and over again, and at every cycle it will be doing some useful work for us. And a typical engine is the Carnot cycle, or an engine that works in this cycle. The idea is you have two heat reservoirs, let's say T1 and T2. Let's assume that T1 is the hotter one. You can model this cycle by a movable piston. So let's say you start in the hotter reservoir, you let it expand, and then you separate the piston. So this is isothermal, this stage. The second stage is you let it expand adiabatically. This is isothermal, adiabatic. So in an adiabatic expansion, since PV to the gamma is constant, it's basically cooling down. And well, you can also say that since the internal energy is being converted into work, the internal energy is proportional to temperature, the internal energy is getting smaller and smaller, so the temperature is getting smaller and smaller. Once it cools down enough until it reaches the temperature T2, you bring it in contact with the reservoir T2. You start compressing it. This is again isothermal. Because we want to have a cycle. The first and the second stage, it has expanded. So now we have to bring the volume back to its initial value. So we first compress it isothermally, and then we have to compress it further, but at the same time we have to also increase the temperature to the initial temperature. So then we just compress it adiabatically. We isolate it, keep compressing. This is the adiabatic. So this is a 4-process engine. And let's see, if you look at the PV diagram, we started having a small volume and a large temperature, so a large pressure. Then we expanded isothermally. Well, isothermal expansion just tells me that PV is constant. Since V is getting larger, the pressure drops. Then we let it expand adiabatically. In an adiabatic process, PV to the gamma is constant, with gamma being larger than 1. So as it expands, the pressure drops faster in the adiabatic process. Then we are now compressing it. Here it is the largest volume. We start compressing it isothermally, and then we compress it adiabatically. This is the PV diagram. Well, we know that let's calculate how much heat the system has used. So this is the adiabatic process. How much heat is exchanged between the reservoir and our system in this process? Let's say A, B, C, and D. So the heat given to the system as it goes from B to C is 0. It's an adiabatic process. Similarly, from D to C, it is also 0. D to A. So let me, from A to B, this will be NKT T1 logarithm of VB over VA. And from C to D, this is NKT2 logarithm of VD over Vc. And keep in mind that this is less than 0, this is larger than 0. Because from A to B, there is heat taken. Let's call this Q1. And from C to D, the heat will be given to the other reservoir. Let's call that Q2. So this is Q1. This is minus Q2. Both Q1 and Q2, I define them to be positive. Well, I completed a cycle. Finally, the temperature is the same as the initial temperature. So the internal energy is the same. Delta U is equal to delta Q minus delta W for all processes. During a cycle, this is 0 because I'm in the finally I'm in the same state as I started with. So the work done by the system is the heat given to the system, which is Q1 minus Q2. We can talk about the efficiency. Well, the efficiency is how much work you obtain from a system, provided that you give some quantity of energy to it. We give Q1 amount of energy to my system, and in return I get delta W of work. This is equal to 1 minus Q2 over Q1, which is 1 minus, well, I already calculated Q1 and Q2. N and K, they are the same. I will just cancel them. T2 over T1 times logarithm of Vc over Vd divided by logarithm of Vb over Va. This is the efficiency. Well, we can do a bit better than this. You see, AD and BC, they are on the same adiabatic curve. But that means that the pressure at the point A, Okay, on an adiabatic curve, we already know that this is constant. But this also tells me that T times V to the gamma minus 1 is a constant, because PV is NKT. Well, A and D, they are on the same adiabatic curve. The temperature of A is T1, the temperature of D is T2. So T1 times VA to the power gamma minus 1 is equal to T2 V of D to the power gamma minus 1. And I can do the same thing for the points B and C. So T1 VB to the gamma minus 1, this is equal to T2 VC to the power gamma minus 1. So these relations just follow from the fact that A and D and B and C, they are in the same adiabatic curve. Well, let's just divide them side by side. Well, if I divide them side by side, what I obtain is VA over VB. This is equal to VD over VC. To the power gamma minus 1, but since both sides are raised to the same power, these ratios should be equal. So those volumes are not just arbitrary volumes. To be able to obtain a closed cycle, the volumes should satisfy this relationship. But that means that these logarithms appearing in the efficiency, they are the same. So I can just cancel them. So I have the efficiency, which is 1 minus Q2 over Q1, which is equal to 1 minus T2 over T1. Well, along the way, we had actually shown that Q2 over Q1 is equal to T2 over T1. So if you have such a cycle, the heat you absorb from the hot reservoir over the heat that you give back is proportional to the ratio of the temperatures of the reservoirs.
Why are you saying that the AD and the BC derivative curves are the same? And how do you know that the constants, that those relations are equal, are the same?
What do you mean by the gammas?
No, the TV power gamma minus 1 is equal to constant. Right?
Okay.
Okay. How do you know that the constant for both cases are the same?
I'm not using that.
But then how do you know that those are the same?
You see, what I know is TV to the gamma minus 1 is the same constant along an adiabatic curve. That is what I know. Okay, so, and I don't really care about what that constant is, but if I'm on an adiabatic curve, that product is constant. For a different adiabatic curve, the constant will, I know that the constant will be different. I'm definitely sure about that. But then what I do, the point A and D, they are equal. They are on the same adiabatic curve, right? So I have this equality, the first line. And similarly, I know that B and C are on the same adiabatic curve, which means that, and then I have this equality. Now, the first line and the second line are not equal to each other. And in fact, that's why I have such a relationship. If they were equal, then I wouldn't get any relation between A and B and C and D. Now let's look at this relationship. What does this mean? Q2 over Q1 is equal to T2 over T1. I will write it slightly differently. This is Q2 over T2 is equal to Q1 over T1. Or let me even change it a bit more. Q2 over T2 minus Q1 over T1. This is equal to 0. Yeah, basically this, I just rewrote the same relationship. Now let's try to interpret this. What does this mean? Well, let's go back to our, or in fact, let me even write this in this form. Q1 over T1 plus minus Q2 over T2. This is equal to 0. I'm just playing around. Delta Q as I go from A to B over T1, which is the temperature as I go from A to B, plus delta Q as I go from C to D divided by T as I go from C to D. This is 0. Well, let me even add some more terms over there. Delta Q as I go from B to C divided by T as I go from B to C. Well, delta Q is 0 along as I go from B to C. So this is just 0. Of course, this is not formally correct. We will make it more formally correct because the temperature is not just a single number as I go from B to C. And let me also add something else. Delta Q as I go from D to A, divided by the temperature as I go from D to A. Remember, as I go from D to A, I'm going along an adiabatic curve. So delta Q, the heat given to the system as I go from D to A is 0. That last term is also 0. But as I said, the second term and the last term is somewhat problematic because as I go from B to C, I don't have a single temperature. Similarly, as I go from D to A, I don't really have a single temperature. Well, that's not really a big deal. I can just write this as the sum. What I do is I have a cycle. This is the cycle I have. Well, let me just divide this cycle into very small bits. Instead of thinking my cycle as made up of just 4 large pieces, I just imagine my cycle to be made up of very small, many different pieces, many different steps. But if this is the case, then I can just write this above sum. Well, the advantage of this having very small steps is that within each one of these very small steps, the temperature is the same. Whether I'm on an isothermal curve or on an adiabatic curve, it doesn't really make any difference. So let's say this is delta Q over T. Well, in the limit as I take the steps to 0, delta Q will go to 0. This just becomes an integral. Along this cycle, the Q, the heat given to the system at each one of these very small, infinitesimal steps, divided by the temperature along the same step, summed over or integrated over a closed loop, is 0. Now this is for the Carnot cycle. So for this particular case, at least, if I integrate dq over t around this cycle, I should always get 0. Well, in this form, it's somewhat limited. It just applies to that particular cycle, let's say to some arbitrary Carnot cycle. But let's just show that it is valid for every cycle, not just the Carnot cycle. Let's just imagine any engine. The Carnot cycle was a very simple machine, so we are trying to generalize what we learned from the Carnot cycle. It just worked between 2 different reservoirs. Let's just imagine any process. Of course, since we are talking about P and V, we are still somewhat restricted in the sense that during the process, the pressure and the volume should be well defined. So the system is, at every state, the system should be in mechanical equilibrium. Well, let's just imagine such a cycle, which has an arbitrary PV diagram. Well, what I can do is, and what I'm trying to evaluate is this one, dq over t, around this cycle. What will this be? That is my question. Well, let me imagine very small Carnot cycles. Let's say isothermal curve and adiabatic expansion, isothermal compression, and adiabatic compression. Now, this is one Carnot cycle. Let me imagine another Carnot cycle right over here, isothermal curve, and then another isothermal compression. Here, isothermal, adiabatic, isothermal. Here, isothermal, adiabatic, isothermal. So these are all Carnot cycles. Now let's see. Let's just look at this intersection. No, sorry, not there. Yeah, even there. Well, in this section, it's adiabatic. There is no heat given to the system, no heat taken from the system. Now, if I sum for each one of these Carnot cycles, I can evaluate dq by t, sum over all Carnot cycles, the red Carnot cycles. Well, I will be essentially adding this one, this one, this one, this one, this one, this one, this one. Well, along the adiabatic curves, there are no contribution to dq, so this is 0. This is 0. This is 0. This is again 0. I obtain this one. So by just summing those 4 Carnot cycles, by summing the integral of dq over t over those 4 Carnot cycles, what I obtain is the integral of dq over dt, dq over t over the blue cycle. Well, the blue cycle kind of resembles my arbitrary process. I can improve the resemblance but by taking smaller and smaller Carnot cycles. And well, here in this result, I didn't assume anything about the size of the Carnot cycles, so I can in fact take the limit as each one of these Carnot cycles goes to 0. And then what I would obtain is the blue curve will be exactly equal to the arbitrary cycle. And the integral of dq over t over that blue curve, independent of what is the size of the Carnot cycles and how many of them are there, will be 0. So although we had started by saying that dq over t, the integral of dq over t around the Carnot cycle is 0, but now we have dq over t over an arbitrary cycle is 0. So does this remind you of anything? So you have some function, you integrate around the closed path, it gives you 0. Potential. So this allows me to define a potential. And this basically tells me that if I integrate dq over t from a point A to the point B, this integral depends only on the points A and B. It doesn't depend on how I go from the point A to the point B. You see, this is different. When we were talking about the heat taken by the system, as the system changes from an initial state A to the final state B, the heat taken depends on how we go from A to B. And similarly, the work done depended on how the system went from A to B. But here we have a quantity which basically is independent of how we go from point A to point B. And this quantity is what we define as SV minus SA. This is called the entropy. So basically, if you have 2 very small points, we can also say that dq over t is equal to ds. Questions? Now we can write the second law of thermodynamics. Whatever the process is, Imagine an arbitrary process. The system doesn't need to be in any kind of equilibrium during this process. Well, of course, if you want to use this at every time, the temperature of the system should be something well defined. This integral is always less than or equal to 0, whatever the process is. Now, there are some corollaries. No, this is for a does this matter? Let's see. Let's just prove this corollary and then let's come back to that. So the increase of the entropy is a consequence of this law. This should be in an isolated system. Sorry?
So a cell wouldn't be included in this?
No. Unless you isolate the cell, it's not included here. Well, let's see why.
Sorry for interrupting. Could you move on to one step before? Is there a variable minus 1?
Where?
The Q.
No.
Not things like this.
Yes.
Equals 0, but entropy increases.
Let's see. Let's see. They are consistent. Well, let's just assume we have a system. It starts from a state A. It undergoes some process, not necessarily in equilibrium, and then it reaches the state B. Of course, since it's not always in equilibrium, it's not properly correct to show any path in the PV diagram. Because of that, let's just assume, invent some path, some dashed path. It doesn't actually go along that path. We cannot really define during the intermediate stages, we cannot really talk about the pressure and the volume of the system. But just for the sake of sketching, I will show it by a dashed line. Of course, this law needs a closed cycle, not an open one. So let me close this cycle by going from B to A through a different process at which at every step I can talk about the pressure and the volume of the system. So what does this tell me? Well, the second law tells me that dq over t should be less than or equal to 0. But dq over t around this cycle, I can divide it into two as I go from A to B, dq over t, and then from B to A, dq over t. This should be always less than or equal to 0. This is through a non-equilibrium process. This is an equilibrium process. Now, the definition of entropy, you see here we define the entropy. But here this definition uses an equilibrium process, or let's say a reversible process, a process which can go in both directions. So it is valid, the definition of entropy uses only the second term. So that second term is actually SA minus SB. This is less than or equal to 0. Or SB is larger than or equal to SA, the entropy of the entropy of the final system, final state of the system is larger than or equal to the entropy of the initial system plus from A to B dq by T, whatever that number is. Now that number can be negative. So the final entropy of my system can actually be less than the initial entropy of my system. But for that number to be negative, I have to extract heat from my system and put it in somewhere else, so the system is not isolated. So if you imagine a cell, a cell in your body, well, your cell is constantly interacting with the environment. In fact, it is constantly producing heat by consuming energy. It's producing heat, and then it is sending that heat to the outside. And by sending the heat to outside, that is dq is negative for the cell, it can keep its entropy at a constant level, or even it can lower its entropy. There's no problem with that. In an isolated system, dq is 0. So the final entropy is larger than or equal to the initial entropy. So the signs are correct. Okay, so up to this point, I try to avoid using the term reversible. But to define the term reversible, reversible basically means a process which does not increase the entropy of the universe. So if a process doesn't increase the entropy of the universe, then it is reversible. Otherwise, it is irreversible. Meaning that if you run the engine backwards, it won't be the same as running it forwards. Carnot cycle is a reversible cycle. So in the Carnot cycle, what happens is, let me plot it over here. The Carnot engine takes some heat, Q1, dumps some of it into the other reservoir. This is T1, this is T2, Q2, and does work. This is W, which is equal to Q1 minus Q2. The same engine, if you do some work on the engine, it will take a heat Q2 from the colder reservoir, and it will just send it to the hotter reservoir. Just reverse the steps. Everything will be reversed. In that sense, it's a reversible process. If it's not a reversible process, let's say, suppose there are friction in the system, friction will create heat, which will increase the entropy of the universe. It's not a reversible thing. So if by absorbing an amount Q1, emitting an amount Q2 of heat, it does a work W, you have to do more than W to run it backwards, to absorb Q2 and give Q1, because some of it will be lost in friction. Okay, there are a couple of more different statements of this second law. Okay, this is the mathematical expression. This is, I said, the corollary. A second corollary. No reversible engine can be more efficient than the Carnot engine. Because basically the system we considered was a very simple system. Maybe somebody comes with an idea of a more complicated engine, which might be more efficient than the Carnot engine. And the second law basically says that it's not possible. Independent of how ingenious you are, how ingenious your machine is, its efficiency cannot be more than the efficiency of the Carnot engine. Well, how to see that? Let's before this corollary, let's leave this aside for the time being. We will prove it in a moment. No engine can convert all the heat or not that one. Heat flows from hot to cold. Well, let's see. Let's just imagine two reservoirs spontaneously from hot to cold. Let's take two reservoirs, one at temperature T1, the other at temperature T2. Let's just assume that an amount of heat Q flows from T1 to T2. What is the change in the entropy? Well, the change in the entropy was the sum of delta Q over T of the system. The first part of the system, how much heat is given to the system? Minus Q. What is its temperature? T1. How much heat is given to the second part of the system? Plus Q divided by T2. And we know that the second law says that this has to be larger than or equal to 0. Or Q times 1 over T2 minus 1 over T1 should be larger than or equal to 0. You can, if you want, you can just imagine an engine that takes the heat from T1 to T2 and without doing anything else. They don't have to be just in touch. Well, let's see. If T1 is larger than T2, then 1 over T1 is smaller than 1 over T2, which tells me that 1 over T2 minus 1 over T1 is positive, which tells me that Q should be positive. So the heat flows from T1 to T2 actually. The other case, T2 is larger than T1, then 1 over T2 is smaller than 1 over T1, which tells me that 1 over T2 minus 1 over T1 is less than 0, which tells me that Q is less than 0. That basically Q less than 0 means that T2 is, in that sketch, I denoted Q as the heat given to T2. That is negative, so heat is taken away from the second part, and it is given to the first part. T2 is the hotter one, T1 is the colder one. In both cases, whether T1 or T2 is positive, the heat always flows from the hotter one to the lower one. Otherwise, it would reduce the entropy of the universe. Now we can come to this corollary. Now, how to prove that? Let's just assume that there exists such an engine. Such an engine exists. So what will it do? It will take some amount of heat. Let's call it Q1 prime. It will dump some of it to the colder reservoir, Q2 prime. And in fact, I mean, it would have been nice to have Q2 prime to be 0. So it converts all the heat into work. And, well, let me just call it Q2. And during this process, it does some work. Let's call it omega prime. Let's just imagine a Carnot engine. It takes an amount of heat Q1, dumps Q2 to the colder reservoir, and it also does some work. And since we are told that this hypothetical, we are assuming that this hypothetical engine is more efficient, omega prime over Q1 prime is larger than omega over Q1. In fact, omega prime will be larger than omega, and Q1 prime will be larger than Q1. They dump the same amount of heat, so the more efficient engine takes more heat and does more work than the Carnot engine. So now let's see. There is this omega prime. Let me just run this Carnot engine in reverse. Let's see. No, let me just make a slight modification. It takes Q1 prime, dumps Q2 prime, and does the work omega, the same omega. And since it is more efficient, for the same omega, Q1 prime will be larger than Q1, and Q2 prime will be less than Q2. No, sorry, Q1 prime will be less than Q1. And Q2 prime is, yeah. Well, I will be running the Carnot engine in reverse. So it will take this omega, take this Q2, and dump Q1 in the hotter reservoir.
We only know that the efficiency of the first engine is bigger than the second one. So what can we like?
Well, let's see. Omega over Q1 prime, this is the efficiency of the first engine. This is larger than omega over Q1, the efficiency of the Carnot engine. So Q1 prime is less than Q1. Q1 prime, W is Q1 prime minus Q2 prime, but the same W is Q1 minus Q2. So Q1 prime minus Q1, this is equal to Q2 prime minus Q2. Now Q1 prime minus Q1 is less than 0 because from the first relation. So Q2 prime is less than Q2. Now, what I do, I have the first hypothetical engine. It takes some heat, dumps some of it to the colder reservoir. It does some amount of work. With the same amount of work, my Carnot engine takes more heat from the colder reservoir and gives more heat to the hotter reservoir. So I can combine them. I can use the first engine to run my hypothetical engine to run the Carnot engine. Now this combined system, what will it do? It will take some heat. How much it will take? It will take a Q2 minus Q2 prime, which is larger than 0. and it will dump it all into the water reservoir, Q2 minus Q2 prime. So what happens is heat is flowing spontaneously from the colder reservoir to the hotter one. Hence it cannot be. So no hypothetical engine can be more efficient than the Carnot engine. Well, let me write one more corollary. No reversible engine can be less efficient than the Carnot engine. It cannot be more efficient, it cannot be less efficient. Well, the idea is basically the same over here. Instead of using this hypothetical engine to run the Carnot engine, use the Carnot engine to run the hypothetical engine, and you will have the same conclusion. Now, any questions on these? Now, let me write the third law. Well, you see, we have if you look at the definition of the entropy, well, this definition of the entropy allows us to calculate the changes in the entropy of a given system, but not the entropy itself. We only have the changes. The third law states that entropy as a function of temperature goes to zero as temperature goes to zero. So since we can only, the definition of the entropy allows us to calculate only the differences, so we can use that definition to calculate the entropy up to a constant. We can always shift the entropy. But the third law prevents that. The entropy of everything is zero, at zero temperature. Now, when we look at statistical physics, it will be more apparent why the entropy goes to zero at zero temperature and why the entropy should increase. And you have probably heard the fact that t is equal to zero cannot be reached in a finite amount of time. It's the consequence of the third law. Now let's give a 10-minute break, and then we will continue.